the series ln of n divided by n and starts from 1 to infinity, can we apply integral test for this series or not? First of all, we need to check to see if the function that we are driving out of this series f of x equals to ln of x divided by x is positive, continuous, and decreasing on the interval 1 to infinity or not. So one by one, we're going to check this. Is it positive? Let us take a look at the behavior of the graph. So when you have ln of x divided by x, the behavior of the graph is just a little bit peaky, but please note that you're focusing on the interval 1 to positive infinity. If you look at the graph, this is our first part to check to see if it's positive or not. This graph behaves like this. The behavior is very similar to the behavior of ln of x. But please pay attention. Here we are taking 1 to positive infinity, right? So basically, what you have is from 1 to positive infinity, the graph is on the positive part of y-axis. For any x more than 1, the function is positive. It hits x-axis at 1. So the first condition is met. What about continuity? Basically, this guy has just one vertical asymptote, right? Or if you look at the behavior of ln of x, you are not allowed to plug in any 0. So basically, when you're talking about the domain is 0 to positive infinity. So this is a continuous function. You can check the graph as well. There is no hole, there is no cut, there is no jump. So for number 2, it is also continuous. Continuous on 0 to positive infinity, which includes 1 to infinity as well. So the second condition also met. What about being decreasing or not? To check to see if it's a decreasing function or not, well, we need to take the derivative to check if this is a decreasing function. We need to check f prime. So what is f prime here? F prime of x. We're going to apply the quotient rule. If you have p over q derivative, it is p prime q minus pq prime divided by q squared. So this guy can be written as the derivative of ln of x times x minus ln of x times the derivative of x divided by x squared, which in turns is 1 over x times x. This is the derivative of ln of x minus ln of x times the derivative of x, which is 1, everything divided by x squared. So f prime of x is equal to 1 minus ln of x divided by x squared. Take a look at your denominator. On the denominator, this guy is just positive. So only thing that you need to check is 1 minus ln of x. But 1 minus ln of x is going to be negative. Why is that? If you set ln of x equals to 1, Well, here you have log with base e equals to 1, or x is equal to e. When x is equal to e, or Napier number that we discussed before, 2.71, 82, and so on, this is this number, all right? When x is e, you get 0. 1 minus ln of x for any value on the interval is going to be a negative value. For any x more than e, 1 minus ln of x is going to be negative. So on the numerator, you have a negative quantity. Negative divided by positive gives you negative. So we just showed that this guy is negative. So for any x more than e, you have a decreasing function. Specify that here. So for any x more than e, f prime of x is indeed negative. So let us apply integral test. Now we apply the integral test. Now let us take the integral of ln of x divided by x dx. This is very simple to work with. If you take u to be ln of x, du is dx divided by x, which is already here. So this integral becomes the integral of u du, which is u squared divided by 2, or ln of x to the second power divided by 2, x ranges between 1 to infinity. If you plug in infinity, the ln goes to infinity. So the integral is divergent. Since the integral is divergent, integral test says the series must be a divergent series as well. So since the integral of ln of x divided by x dx is getting closer and closer to infinity, so the series of ln of n divided by n starts from 1 to infinity, also diverges to infinity. We have a divergent series. So let's recap what we did. Here we have the following series, the summation of ln of n divided by n starts from 1 to infinity. Can we apply integral test? To apply integral test, we need to check to see if the function that is the same as our general term follows the following conditions or not. Is it positive? Is it continuous? Is it decreasing on the interval 1 to infinity? Well, this is my function, ln of x divided by x. If I check the graph of this function approximately behaves like this, right? In some part, but it continues to the right-hand side. Obviously, the function is positive on 1 to infinity. The function is continuous on 0 to infinity. It is decreasing. Why is that? Because when we take the derivative of this function, applying the quotient rule, the derivative becomes 1 minus ln of x divided by x squared. X squared is positive, 1 minus ln of x is negative. So on on e to positive infinity, this function is a negative function. It means that you have a decreasing function. So when you have a decreasing function, it means that you can apply the integral test because all three conditions are met. Instead of working with series, you can work with the integral itself, the integral of ln of x over x dx, when x ranges between 1 to infinity, using a simple u sub, u is ln of x, du is dx over x, can be written as ln of x to the second power divided by 2 when x ranges between 1 to infinity. But remember the behavior of ln of x. X goes to infinity, your ln goes to infinity. So here, your integral diverges to infinity. So by using the integral test, our series also diverges to infinity.